Good afternoon, everyone. On behalf of the U.S. Commercial Service in partnership with the Connecticut District Export Council, we welcome you back to our part two of our PFAS series. We held part one a couple weeks ago, and we're happy to for you to join us again for part two, PFAS Technologies. Again, my name is Tony Sargis. I'm an international trade specialist with the U.S. Commercial Service, and I will be your host for today's session. Just brief introduction on the speakers, and then I'm going to cover a couple housekeeping items, and then we will begin the formal presentation. Joining us again is Alfredo Fernandez, partner with Shipman and Goodwin. He is also a Connecticut District Export Council member. Thanks for coming back, Alfredo. And Brian Drollet, managing environmental scientist with Exponent out of Boston, Massachusetts. Before we begin today's formal presentation, again, I'll cover a couple housekeeping items. Just want to plug Export Week for everyone out there. So we will be hosting our annual Export Week event May 2nd through the 6th. We have over 25 sessions planned for the week. You can see the specific details on the website, trade.gov /US Commercial Service Export Week, but in different disciplines such as industry-specific opportunities, international sales and marketing sessions. We have a 5-part series on export finance, and then we're going to be hosting various export compliance and documentation sessions as well. Just a couple other items. Everyone is in listen-only mode, so we will open up microphones for the Q&A towards the end of the presentation, but we also encourage you to write your questions into the Q&A feature. Lastly, the views and opinions expressed in today's presentation may not necessarily reflect the official policy or position of the U.S. government. Again, this webinar is being recorded, so if you object, please disconnect at this time. I'm going to pass the ball over to Alfredo to begin. Alfredo, you should have control in a minute.
Okay, looks like I'm in control. Good afternoon or good morning, everybody, depending on your time zone. And thank you for joining us for part two of our session, PFAS, the mini boot camp for exporters. A couple weeks ago, about a month ago, we had a part one that was focused on the basics of PFAS, and that's per and polyfluorinated alkyl substances. That we call it PFAS for a reason, because the long version is too long. But the goal of today's session, part two, is to focus on the technology piece around the various elements of PFAS considerations. Brian and I attend a lot of these things, whether we're presenting them or attending them as a participant for education. And we discussed, we hadn't really seen a technology-focused session. And our goal for part two today was just to present something that hopefully is different for a lot of folks that maybe have attended some other types of PFAS sessions. The basics are everywhere, and hopefully some of the attendees today are returning from our part one with that baseline. But today's goal, as we mentioned, will be to explore a couple different areas of PFAS technology. Of course, none of this is fully exhaustive, and Brian and I aren't necessarily experts in any single one of them, but because we are addressing a lot of these from cross-disciplinary viewpoints as legal and technical advisors, we do, pick up enough things about enough topics to be able to present this session and give folks kind of a lay of the land of where things stand and a preview of where things may be coming. Obviously, some of you may be very into one of these specific areas based on the attendee list. There may be some specialized companies there. So if there's anything anyone from the audience kind of wants to add as we go through these sessions, use the Q&A as a kind of a comment thing. And if there's a chance for us to weave it in, we'll absolutely do that if possible. So in terms of where we're heading today, we're going to kind of look at EPA's strategic roadmap that was released not too long ago and get an idea of where the federal regulators may be going with PFAS generally, and then where technology fits into that. We'll address some of the current consumer product issues and technologies. We'll get into some of the standard analytical methods, which is an evolving world in terms of what methods are available to test for PFAS. We'll get into some site characterization issues, treatment, fire suppression, AFFF type stuff that gets a lot of headlines, forensics of determining where certain PFAS may have come from or where they didn't come from. and then wrap up with something to take back to your company with some business takeaways at the end of our hour. So, in terms of that first agenda point, EPA strategic roadmap, back in October, I think 2021, EPA released this roadmap that covered various offices and areas of focus for PFAS generally, and how the EPA as a big organization was going to break it down in terms of handling and managing PFAS as a regulated or soon to be potentially regulated substance. The broad goal in our first bullet here is that they want to, well, there's various goals here. We kind of filtered it down to those pertaining to technology and R&D. EPA's goal in that respect is to increase the understanding of exposures, human health, ecological, environmental effects, and what actually works based on science to treat those from a health perspective, from an environmental and kind of land impact type science and business operations, et cetera. So in that roadmap, various EPA offices put together what they're doing for PFAS, and I'm just assuming folks aren't particularly or very carefully familiar with that product. So again, keeping it with a couple selections, and this isn't an exhaustive list by any means, but with a focus on technology today, the Office of Water, for example, will be looking to use a effluent limitations guideline program to minimize PFAS discharges in industrial facilities. The technology to do that, is not really there today, but we're curious to see where that goes based on that goal. And then that office is going to establish technology-based regulatory limits. So really, those limits are going to be tied to the state of technology as it evolves from 2022 and onward. Similarly, on the air side, one of their goals is to figure out cost-effective mitigation technologies in terms of air dispersion from facilities working with PFAS that get into the air and they settle on surrounding land and water, its crops, et cetera. And then their Office of R&D is putting a lot of money and people into just researching PFAS generally to have more data and more information or in terms of how to handle PFAS in the various media and the various potential stakeholders there. So that's a little bit of a little bit umbrella of where EPA's strategic roadmap points our curvy road in terms of how technology may be playing a factor in that overall plan. Obviously, the states have their own thing, but we don't have time to go through all 50 states, and not all 50 states have something that neat. In terms of the regulatory standards, as technology has been improving, detection equipment improves, lab methods and lab equipment improves, as the sensitivity of equipment evolves, the limits that can be detected are improved down to smaller and smaller and smaller detection levels. And part one, we mentioned a lot of these things are measured in parts per trillion, which is orders of magnitude smaller than parts per billion and parts per million that a lot of other traditional contaminants are measured at from a health effect and equipment detection effect. Even California's proposed, kind of ideal limit is in the parts per quadrillion, which is just hurts the brain to think about how sensitive that detection equipment would be and how clear the technology would have to be to make that commonplace, which is doesn't seem to be the case today. All this under the stage that the background levels are not really known as to what's out there in the world and what's just kind of normal after 30, 40 years of man-made, spread of PFAS and all types of media that have gotten into rainwater, into the snow and ice on top of Mount Everest. Is just, even though man-made, it's really quite everywhere. So determining how a particular site or a particular material is relative to what has become background level is still an issue that needs to be worked out. And as technology improves, I think that'll be made more clear over the years. Similar to that, this is just a concept chart here. As the technology has improved, as medical research has improved, a lot of various states and the federal government have started from the 500 ppt level to lower and lower, 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 and often single or double digit ppt um, levels. Again, just a trend as technology improves and understanding improves. The drinking water here for PFOA specifically have dipped down, and states tend to kind of want to outdo the last state in terms of going lower than the last person that released a new rule. But we're seeing a lot in the single digits, 20, 30, 50 ppt, and we'll expect to see more refined levels going forward for other states as well. We'll start our first kind of breakout topic with the consumer in mind, and this may not apply to your particular business today, but it may apply to you in a personal capacity, and then we'll get into more kind of industrial commercial considerations after this section. But as a human being living in this world, you're exposed to PFAS. I am, Brian is, and it's everywhere really. A lot of what we're seeing now in terms of technology, lack of a better term, is advertising that things are PFAS free. My wife, for example, asked the other day for a PFAS free frying pan, and I found one that said PFOA free, and we got it. But I said, just because it's PFOA free doesn't mean it's PFOS free and all the other list of a million PFAS or 9,000 PFAS. So the consumer product awareness and understanding how claims of PFOA free can be made, and broader claims like PFAS as a giant group can be made are questions that never really mattered until recent years. And our question for some discussion and exercise here is, what does PFAS free really mean? What does it mean for the seller? What does it mean for a consumer buyer? Who decides? Should a regulator decide what a PFAS free claim needs to be? We don't expect enforcement of this altogether very soon, as some agency may have to step up and say, I'm gonna regulate PFAS free claims, like some people regulate BPA free and things like that, or alcohol free type claims. So it may not be EPA. And then as we were doing some research in this area as well, we found a kind of a paradox where a lot of what would otherwise be considered kind of an environmentally conscious product, like those paper straws, are actually PFAS sources themselves, because paper, for example, in and of themselves, are not very good at holding liquids. So there is a little bit of a coating inside some of those paper straws, which may have some PFAS in there at low amounts too. So you get to pick which environmentally friendly consideration is more important to you, because it seems like you can't have a perfect product as a consumer. On the food packaging issue, as in COVID specifically, a lot of folks have probably had plenty of takeout type meals because of some restaurants are closed or whatever. But a recent Consumer Reports study put a lot of the food packaging on blast pretty hard. And a lot of the French fry bags, the burger wrappers, the salad bowls, the burrito bowl type things detected with PFAS based on some studies. And Brian will get into what kind of qualitative methods they may have used in this Consumer Reports study to figure that out. But I think it brought a little more mainstream attention to PFAS, and that gets in my food, and I eat that food. And that our little schematic in the top right corner there shows the various ways that PFAS from food packaging is a concern, either directly to the human through the food, or as waste. It gets into a landfill, it may leach, it may be blown away in the wind into the environment, into the crops, and then back into you as a health risk. So and that's a kind of a very easy concept to understand for the general consumer public to be weary of PFAS, and maybe it starts them getting more interested in learning more about it. And we'll get a little bit more into that later as well. Some states were seeing some outright bans for intentionally added PFAS to food packaging. Connecticut, where I sit, is one of those states, and there's about a dozen or so similar ones, and more expected. And FDA has a website as to when it has approved PFAS in certain, uh, what they call responsible applications, and based on qualities for particular food packaging. And there is a bill in the U.S. Congress to ban PFAS in food packaging, at least though PFAS intentionally added to products for grease resistance and things like that. It's just been introduced to the House. Not sure if it's going to get anywhere or die there as a bill, but something to keep an eye on there as well. In terms of what's next, as we mentioned, there's going to be some companies, particularly large fast food type chains that you've heard of, are voluntarily phasing out PFAS containing materials, wrappers, containers, etc., from their supply chain. It's going to take a couple of years just based on the realities of the supply chain, but they've pledged to work those out. You could Google a few names and see some news, and the mandatory phase outs for particular states that have focused on food containers, or if you may remember from phase our part one session, the state of Maine will have a full PFAS ban within the decade. Substitute products are in discussion as to they have to replace that stuff with something in all likelihood. Are the substitute products going to be any safer? What kind of testing goes into whatever they decide is PFAS free? And how's that been tested? So an open question on technology for substitute products there. And then lastly, on the consumer piece, as mainstream awareness of PFAS becomes greater and greater, which we expect it to be, the availability of consumer information about their products, what they're buying, where the PFAS may come from, what the supply chains look like. It's kind of a growing area of technology, particularly for the millennials and younger generations, to be able to scan a product at the store, see where it comes from, see where the risks are. There's plenty of other apps for it for more traditional toxins and things. But PFAS is the next logical step for how some of those resources and databases are going to be relevant. So I'm going to hand it over now to Brian, who's going to discuss some analytical methods, both the kind of the lab stuff that will get you some exact numbers, and then some qualitative type tests that may not give you as granular as information, but still useful in kind of a litmus test, so to speak. So Brian, go ahead.
Thanks, Alfredo. So I want to just go back to the theme that you touched on earlier about the kind of the race to the bottom. So we have lower and lower regulatory limits, and those necessitate better and better analytical methods so that we can actually detect down to the level that we're regulating. But on the flip side, our ability to measure PFAS in lower and lower concentrations, that also enables regulatory limits to be kind of set that low. So there's a little bit of a chicken and the egg problem there, but maybe one of the biggest takeaways from this talk is that there's a lot of standard validated analytical methods out there to measure PFAS in one sample or another. However, those methods really only target a small subset of PFAS. So the graphic on the right helps illustrate that point. You imagine the entire triangle being kind of the universe of thousands of different PFAS that are out there. Our early attention really only focused on two of those, PFOS and PFOA. And then over the past maybe 2 decades or so, better methods have evolved that allow us to explore a small slice of that pile. But nonetheless, more of that triangle in either kind of a quantitative or a more qualitative type analysis. Fred, if you go to the next slide, just a brief touch on some of the standard analytical methods that are out there. And those are the ones that I call would be established or endorsed by various agencies, whether it's EPA or ASTM. So your water sample could be characterized today for about 40 or so PFAS using a standard analytical method. Most method development was really focused on water, as that's kind of a low-hanging fruit for human exposure. But there are obviously other methods out there that can detect PFAS in solid samples like your soil or sediment or tissue. And you'll note that EPA method 1633 covers a lot of the bases. It's here on this slide quite a bit. That method was just recently published in draft form, and it can target 40 different PFAS compounds, which is the most that we've seen to date from a standard EPA method. So it's still under lab validation. And another interesting facet about this particular method is that it's the first Clean Water Act type method available to monitor wastewater. So that's going to have some important implications as we now expect wastewater permits to start mandating and for monitoring in compliance with the permit.
Yeah,
Next
one of
slide.
the
Oh, sure.
Brian, one of the takeaways there for business is that of the 9,000-ish PFAS compounds, really there's only approved methods or almost approved methods, sorry, for roughly 40 types of the compounds, right? So even if the question of how do I actually test for all those things is a real head scratcher because the methods aren't there or haven't been validated for anything other than this very small subset, even though that subset has grown from 2 to 40 of the total PFAS picture. So a big stumper, a big challenge of technology today, but something we expect to be expanded going forward.
Good point. So as I mentioned earlier, really we only use to target two compounds, PFOS and PFOA, in our environmental samples. And that starts to come across in this figure on the right. I've summarized some statewide groundwater data from Maine. In the early 2010s, only PFOS and PFOA were monitored, if PFAS was monitored at all, in some groundwater samples. That number of compounds began to increase over time, concurrent with the availability of other methods that were out there. And it seemed to kind of follow EPA's timeline for method publication. So in 2009, EPA first published method 537 that targeted 14 compounds. That method got an update. Method 533 came out, and now today with 1633, again, we can measure about 40. So this consideration of method evolution is really important, especially for early site characterizations that we're evaluating today. Probably best noted by Massachusetts DEP with this quote here that before September 2009, there weren't any validated test methods or standardized data quality criteria. So DEP cautions that any of that older data that's generated might have limitations and should be used with caution. So if we go to the next slide, Alfredo, some, if not many of you in the audience, you might not deal in the world of environmental samples all the time, but maybe more consumer products. So I'll briefly touch on some of the methods that exist to kind of do a more, I would say, qualitative characterization of PFAS and kind of why you might want to use them in the first place. So I've listed a couple of here that, for example, the total oxidizable precursor method, or the TOP assay, that starts to answer the question of how much PFAS in your sample is a precursor or something that might degrade in the environment to a more terminal type PFAS like PFOA. The total fluorine method is one that just generally tries to answer the question, is there fluorine on the surface of your product or your material? The total organic fluorine method, it tries to extract any organic compound that has fluorine on it to just generally answer the question, how much organic fluorine do you have in the sample, not necessarily individual compound specific. And then there's non-targeted analysis, which I won't get into anymore in here in these slides, but essentially we're using really high-tech laboratory technology paired with some pretty insane data analytics to try to understand what individual molecules are in our samples that we didn't identify with a standard method. So that's much more in the R&D type world, but we do see, like, for example, EPA doing this more and more and publishing on it. So I want to just touch on a couple of these methods in more detail. So for the top assay, this total oxidizable precursor assay, essentially you take your sample, you oxidize as much of the PFAS as you can to turn everything into a terminal type compound, or one that probably won't degrade in the environment anymore. The figure on the right, it's busy, but the point here is that if you measured a couple of, for example, AFFF samples, you might not find a lot of the PFAS compounds that we routinely monitor for in some of these older AFFF formulations. If you run those samples through the top assay, you're going to break down those precursors into the terminal forms. And then on the right, you can see that after oxidation, you're going to measure these later on. So this gives you a sense of how much could be in your sample, and if they were released into the environment, could contribute to the burden of, say, PFOS or PFOA later on. Now, on the next method, but total organic fluorine, this method obviously measures exactly what it says, any organic molecule that contains some fluorine. And this tells you how much, if any, kind of uncharacterized PFAS you might have in your sample, or kind of perhaps the abundance of all the molecules that you can't really quantify with a standard method. The graph on the right is an example of the concentration of some various PFAS classes, the orange, blue, and the yellow, that we routinely look for in a targeted method. And then the tall black bar is the amount of organic fluorine type compounds that are still remaining in the sample. So it might not look like you have a lot of PFCAs, or the carboxylic acids, in your sample, but you could have certainly some more organic fluorine left over. And then finally, the total fluorine method. If you go to the next slide, Alfredo, I'll just briefly touch on this. Here, we're basically shooting lasers at a material surface to see if there's any fluorine at all, whether it's organic or not. And applications for this are really to screen surfaces like your raincoat or any of your consumer products to see if it has fluorine. And then that might inform you whether or not you would want to do further investigation into whether it has any of these particular PFAS compounds that we routinely talk about. I know that this method is also under development for some rapid field screening of contaminated sites as well, where you would take, say, a groundwater sample, you would pass it through a filter, and then you would run a total fluorine analysis in the field on that filter to see if it caught anything. And on the next slide, I'll pass it over to Alfredo now to talk about some of the site characterization and remediation techniques that we use when we're evaluating sites.
Thanks. And on that last one, that last method you use, I think the idea of some field testing and field screening is an important piece of where the technology is heading, as opposed to just given the cross contamination risks that maybe we'll hit, I think, in a few slides. If it can be done right there with some pretty quick, at least rough cut type information, I think that's something to expect to see more and more of. So with our next breakout here is the assessing a site for the presence of PFAS, more from an environmental soil and groundwater perspective as opposed to inside the buildings. But because PFAS are not yet designated as hazardous substances, the ASTM method doesn't require that an environmental consultant actually address PFAS in any kind of phase one environmental site assessment. That's kind of the go-to scope of work for when you're evaluating a site with due diligence, as primarily a desktop search of databases and a site walk without any invasive testing. It's just what's readily available without picking up a drill or a shovel. ASTM's method was recently revised to suggest or at least provide guidance for the opportunity for the consultants writing the phase ones to address PFAS um, as out of scope considerations uh, or something like that that technically is not in the scope of ASTM because it's not a hazardous substance with capital H, capital S, as is required by the method. So we are starting to see some consultants, when it makes sense, address PFAS in phase ones based on an assessment of site history, what's adjacent to the particular target site, what kind of operations have occurred, what kind of manufacturing has occurred. And some states do already list them as hazardous substances. So on a state by state basis, there may be some more specific requirements for a phase one. So we are starting to see that. Usually the buyer or a lender's consultant, if they're the ones undertaking the phase one, will want to push a lot of that in there. The seller, on the other hand, probably would ask its consultant to not go there because it's not required, and for purposes of selling a property, the less trouble, the better. All right, I think I've hit my points here. We'll keep moving here. After the phase one, occasionally there's a need to do some field work or some more invasive testing. Again, sometimes that's buyer, sometimes that's seller, or sometimes that's just in the context of a regulatory program without a transaction specifically tied to it. So there are field contamination issues, lab cross-contamination issues, and by that we mean something other than what is intended to be tested puts PFAS into the sample so that it's a false positive, not indicative of the water or the soil that was actually picked up. So given the ease of cross-contamination and the PPT levels that we're dealing with, many consultants have advised or revised their protocols and policies for when they are undertaking PFAS testing to minimize the risk of cross-contamination. A couple state environmental agencies have also put out guidelines for what to do. Just for a couple ideas of themes that we're seeing in there, field personnel are not to wear waterproof or waterproof treated materials or gear. That's Gore-Tex boots or jackets, waterproof paper for notebooks, waterproof ink type stuff, which can introduce PFAS into the sample. Again, Teflon as a brand name of historical PFAS materials shouldn't be on or near the person collecting, or even in the vehicle. Scotch guarded seats would get onto the clothing, and somebody wipes their hand on their jeans or whatever. We've seen issues of cross contamination there. Some of the just equipment in the lab or in the field, pumps and tubes and glassware, depending on how it's been cleaned, et cetera, can be a cross contaminant risk. And LD polyethylene has been recommended to be phased out because of the higher likelihood of cross contamination there. Some of the recommended replacements or the preferred materials, plain cotton clothing, regular old paper, regular ballpoint pens that aren't necessarily treated with kind of waterproof characteristic additives. And then high density polyethylene equipment has been recommended. But not too long ago, after I first created this slide, EPA put out a kind of a general open letter regarding some potential issues with HDPE containers. So maybe that recommendation isn't perfect in and of itself, but TBD. In terms of dealing with what you find out there in field work and invasive sampling, or in a remediation project where soil has to be moved or wastewater has to be removed, it really depends on the facts there. What are you actually trying to remediate or dispose of? And depending on your state or jurisdiction, certain levels may apply. Where 20 miles down the road, you'd be dealing with a very different state level, even though you're in the same general area. And dealing, figuring out what the target is can be confusing for a lot of people. And then as you're testing, understanding which exact compound are we actually testing to, what's going to drive our limit, what's going to drive our success criteria for remediation. And in terms of water, for example, there's granulated activated carbon or GAC filtration systems that are, proving to be some of the most used water treatment type technologies for municipal water plants, for example, where there's an issue with the source water. There's some GAC filtration step that gets levels back under the applicable drinking water standards there. And, in terms of, often our clients say, how much is this going to cost? It's a guess. I mean, there's really no way to guess how much a remediation project could be, just based on how varied the data could come back with, and the particular media involved and particular site unique considerations to keep in mind. So it can be, you could assume it's going to be more expensive than you think. That's a pretty safe bet. But how much more expensive is for anyone's guess.
So this figure from EPA, I like it because it highlights the general life cycle of PFAS, from the manufacturing to its use in products to disposal and then ultimate treatment of any product or associated contaminated media. And the common questions that we ask are kind of, where is the waste? How do we treat it? And what do we do to prevent the PFAS from entering the environment in the first place? But when it is in the environment, generally we need to do something about it. So there are treatment options available, and I'll touch on a couple of different technologies on the next slide. When we're considering, if you want to move to the next slide, Alfredo, when we're considering water samples, there's a few, I would say, I would kind of call them off-the-shelf technologies. They're already kind of well established that we can employ to remove the PFAS prior to consumption, or even prior to release back in the environment if we're trying to treat groundwater, we're trying to treat surface water. These are all common water treatment techniques that you've probably heard of before, and they're generally effective at treating PFAS, at least according to the EPA, which I'll touch on in a bit. And you've probably heard of them because they're some of the same technologies that you might employ in your own home water treatment system. So I'll just briefly touch on them. Granular activated carbon, Alfredo mentioned it earlier, but here we have a carbon-based media, and the PFAS adsorbs to that carbon. And it's really effective at scale to remove PFAS down to low levels. It's more effective for some of the longer chain PFAS compounds than it is for the shorter chain PFAS compounds. But nonetheless, it's probably the most widely used water treatment technology for removal of PFAS. Ion exchange resins are also quite popular. These can be single use or regenerative. So here, just briefly, the resin itself is positively charged, and that's going to attract negatively charged PFAS when it comes in contact with it. And it'll also, it can absorb some of that PFAS from the hydrophobic tail onto the resin itself. So it's more effective for certain classes of PFAS than others. And I've seen some applications where the ion exchange resin and the GAC media are mixed together for kind of a two-stage treatment in one. But nonetheless, it's definitely an effective technology. And then finally, reverse osmosis. And you've probably heard of this in context of desalination technology. Here, water is just passed through a membrane, and the chemicals that are in that water are rejected and they go to a waste stream. So RO still requires some sort of pretreatment to help reduce fouling of that membrane. And as far as water treatment goes for PFAS specifically, I believe this is still under development for more large-scale drinking water applications. But nonetheless, it's identified as a highly effective technology by EPA. If you go to the next slide, Alfredo, at the more consumer level, we can think of PFAS treatment in water in two concepts. One is point of entry treatment. We call those POET treatment systems, or point of use. The nomenclature really explains it all. A POET system is what you would use to treat the water coming into your building, and then every single tap in that building has treated water. And then point of use might be synonymous to your countertop water pitcher, or kind of what you use to treat water before you drink it. And I'll touch on those two in a bit more detail. On the next slide, talking about point of entry treatment, generally it has a couple of stages like you see in the diagram. Perhaps there's a pre-filter to remove any sediment, and then it could have 1 or 2 stages of granular activated carbon filters, maybe followed by an ion exchange resin or RO if it's a really kind of sophisticated system. And again, this is where water comes into the building, and then it's treated before going to all of the taps within the building. Kind of on the other side of the consumer treatment is the point of use treatment. Here, water is treated immediately before it goes to the user, and this might be synonymous to those under the sink systems that you see in the picture here, or again those countertop filters. So it's essentially similar to the whole home treatment, or even the field scale treatments that we use at contaminated sites, just on a much smaller scale. And for the consumer, there are products that are certified by NSF as effective at removing at least PFOS and PFOA in a water sample. So and I've linked to that NSF certification here. It's basically a database where you can type in a contaminant and see if NSF approves any different products as being effective at that treatment.
Yep.
On the
And
next slide, go ahead,
not all pout filters are created equal. You have to dig into their available information to figure out, okay, this one actually is effective for specific PFAS compounds.
Mm-hmm.
Others, that are lead and metals and things like that may not be validated for any PFAS.
That's a great point. Could require a different type of treatment technology. But when we're talking about PFAS, or I guess any other drinking water contaminant, there's loads of information out there about how effective the various technologies are. And one good resource for the consumer is EPA's treatability database. So here the user can select a common contaminant and see how effective some various treatment technologies are. As an example, for PFOS and PFOA, you can select those within EPA's database, and you can see that there's high efficacy of granular activated carbon and ion exchange and reverse osmosis. But common treatment techniques like biological treatment, chlorination, sand filtration, which is commonly employed in municipal drinking water treatment systems, are kind of judged by the EPA as being quite ineffective at removing PFOS and PFOA from a water system. And I've linked to the EPA drinking water treatability database down below. So that kind of covers the gamut for water, and I'll just want to quickly mention treatment for solids. For solid waste, whether it's soil, sediment, any other contaminated media, there aren't too many more options out there compared to what we have available for water treatment. Contaminated soil could be treated, as we would say, in situ, or rather than just excavating all of it and putting it in a landfill. We could mix that contaminated material with an amendment like granular activated carbon that will help sorb those PFAS compounds to it and keep them from leaching out of the soil and migrating offsite. So this is a non-destructive treatment technology. Obviously, if you have contaminated soil at your site, you can just dig all of it out and backfill the hole with some clean material. And then you also have to take that excavated material and dispose of it somewhere. Whether it needs to go in a permitted landfill or not is kind of up for debate, and potentially will change in the next couple of years with new regulations. But this is a non-destructive technology as well. You're just taking the PFAS from one area and you're moving it to another. There are incineration techniques that are gaining a lot of attention as of late. So solid material like maybe your spent granular activated carbon or your contaminated soil, or even liquids like AFFF formulations or landfill leachate can be burned in commercial incinerators or high temperature kilns at thousands of degrees Fahrenheit. Doing so, you the goal is to oxidize as much of that molecule as possible without having any of those terminal PFAS compounds remaining and perhaps being lost in the emissions from that particular facility. But it is certainly an area of ongoing research as AFFF take-back programs are more and more popular, and just trying to figure out what do we do with contaminated material.
Yep. And just a quick note too on the in situ treatments. We're seeing not on the slide, but some kind of university projects to figure out how some of those technologies can be improved, including so what we've seen like some liquid injections and then to absorb some PFAS materials, and then they're extracted out as a liquid. So, kind of cutting edge type things, but not sure how ready they are for the mainstream. But it is an area of ongoing research and some business ventures. We're going to start showing up there.
So finally, I touched on this a bit earlier, but if you remediate your waste, say by excavation at your site, and then you need to figure out what to do with it, or if you have granular activated carbon or an ion exchange resin that needs disposal, you need to figure out what to do with it, whether we incinerate it or whether we send it to a hazardous waste landfill, or even in some instances, contaminated liquid undergoes deep well injection. So just putting it, I guess, back underground deep enough so that you hope you never see it again. So this is kind of the state of the art of what's out there for being able to get rid of material that's contaminated with PFAS. And as we've said plenty of times already, it's certainly an area of ongoing research. There's a lot of cutting edge technology that's coming out lately to try to deal with this problem.
Okay, so our next breakout topic is fire suppression. AFFF is the acronym you're familiar with. That's aqueous film forming foam products that are that do use PFAS, at least historically. And we mentioned a little bit of this in our first session, but the functional value of the AFFF foams is that they spread on top of fire like a blanket to suppress oxygen and the conflagration of the flames. There are some military specifications, for examples, that require certain characteristics based on chemistry and compliance with some of those military specifications, or mil specs, are required for some facilities. So not to rehash a lot of what we covered in the first session, but in terms of where the technology is moving, as states are starting to phase out AFFF altogether. Just new products can't be introduced. Everything needs to be replaced with PFAS-free foams, etc. On a state-by-state basis. Again, it's probably less than 20 that are actively there. And but anyway, a lot of facilities are driving the market for PFAS-free products for foam, and some states are realizing that we made you have AFFF as requirements, or the federal government made you have AFFF foams as a requirement. Establishing some take back programs so the facilities aren't necessarily financially burdened as much as they otherwise would be if these weren't government driven requirements, such as airports and military bases. The Department of Defense has announced that it's going to be phasing out military uses of PFAS containing AFFFs in the next couple of years. So some of those last holdouts and the FAA and the military are kind of different beasts, but have an eye on the prize of phasing out PFAS from some of the required AFFF requirements or obligations. So some PFAS-free foams are under development. We are, catching wind of new markets, new product entries that are appropriately there for the market as it shifts to PFAS-free chemistry. And the tricky part is some of those PFAS-free alternatives, although attractive from an environmental and potentially PR standpoint, may not actually meet some of the mil-spec requirements that they have to do. It's a must-have, not a nice-to-have for certain facilities. So there are some alternative categories like fluorine-free foams, protein foams, fluoroprotein foams, and film-forming fluoroprotein foams. Thank you, Brian, for putting that list together for me. But there are a couple agency research arms that are investing heavily in the PFAS-free foam, world as to what is the future of this going to be, and are the alternatives actually better than the products they're replacing, which is always a tough question.
So finally, I'm going to wrap it up with our last topic, and I'll try to move quickly so we can save some time for questions. And I just want to touch on kind of the world of environmental forensics as it relates to PFAS. On the next slide, Alfredo, just generally, forensics is kind of the application of different scientific methods to identify how and why contaminants might have been released into the environment. We want to know things like kind of what contaminants are there, how much are they contributing to a particular remedy needed at a site. We want to know how different is that level of contaminant compared to just what's generally there in the background. We want to know when it got there, obviously, and if we can, try to reconstruct the pathway where this contaminant actually went to the environment. So on the next slide, I've kind of shown how we kind of need to make some special considerations for PFAS. When we want to identify the contaminants and perhaps generate a PFAS fingerprint in a sample, the standard forensic PFAS methods are still evolving. So as we touched on a lot earlier, we're only measuring for a handful of samples, and if we can build up that, we're only testing for a handful of compounds, and if we can build up the number of analytes that we routinely look for, we can start to evaluate patterns of this is the particular fingerprint from this type of industrial operation or that type of product. When we try to distinguish from natural background, we've mentioned earlier that the environmental ubiquity and persistence of PFAS, we see them everywhere. So we need to really analyze what's different between the concentrations that we see in our samples compared to what's just there in the background. And then obviously some of those PFAS compounds as precursors could degrade to more terminal forms of a PFAS. So delineating release timeframes, we need to be really careful about that. And then obviously we need to know what industries are associated with PFAS and the types of chemicals that they're using or the products that they were using, which could ultimately shed some light on how they were released to the environment.
Yeah, and from a legal perspective on this slide, we haven't seen it too much yet, but where things are going with litigation generally and increased regulation, there's going to be a need for some specialist forensic type specialties to be able to kind of fight about is that my PFAS or your PFAS, and who's really responsible. And some of these techniques, we use the term fingerprinting, where in traditional contaminants, where based on breakdown data, et cetera, you can kind of figure out when it was when it was released to the environment, et cetera, to forensically rule out or rule in certain types of possibilities for who's responsible for that particular contamination. And with that point too, and I'll mention litigation. Well, I'll save it for our next slide, but wanted to point that out from a, parties disputing or a party that's been put under some kind of remediation requirement by an agency. There may be some workarounds based on forensics as that technology improves.
Mm-hmm. Yeah, great point. So moving on, probably the most technology advancements that we can get in the world of forensics is just better analytical methods. I showed this figure before where really we only looked at PFOS and PFOA, and that gives certainly some information, but not as much as we would generally like. So as the number of analytes increases with standard methods and non-targeted methods are employed more and more, it just helps enable a more rigorous forensic analysis. Alfredo, you can go to the next slide, and I'm just going to really briefly touch on this. When we have a better data set, we can do some kind of fancy things like nice statistical analysis to pull out fingerprints. That's really all I'm going to say about it in the interest of time. But one thing that I do want to point out, actually, if you go back to the previous slide, Alfredo, was the fact that last month, EPA published their national PFAS data sets. It was about a month ago now that they came out with them, and that gives a lot of information on facilities that EPA has in their databases who may have been handling PFAS, or who are the manufacturers and importers registered under TSCA, or who's discharging into the environment that we're monitoring for. And that is free. That information is available to the public, and it's quite useful from a forensic perspective.
Yeah, very, very powerful tool that just came out.
Mm-hmm. And then finally, kind of where are we going? Well, we've seen since maybe the early 2000s, there's been a shift generally from more of the longer chain PFAS chemistries to shorter chain PFAS chemistries. And now we're seeing replacement chemistries that look similar to, I would say, those legacy PFAS compounds, but maybe have a couple of substitutions, like maybe there's a chlorine instead of a fluorine in a certain area. So trying to stay up to date on what manufacturers are producing for specific applications is really important, and something that we're definitely keeping an eye on. And then if you just want to get away from PFAS altogether, there are certainly products that are trying to gain the same functionality as a fluorine-containing product to do the same thing. For example, a polyurethane-coated textile for like a rain jacket for water repellents might have similar characteristics to a fluoropolymer that was treated. You might be familiar with ceramic coated cookware instead of like Teflon coated cookware. Trying to achieve those same benefits of the surface properties without necessarily containing fluorine. So that's certainly an area that's new and it's evolving, and it's one that I think we should all be keeping an eye on. And with that, I'll turn it back over to Alfredo for some wrap up.
Sure.
So
this is our last slide before we'll try to tackle a couple questions that have been coming in over the session. In terms of takeaways, if you're leaving with something today, leave with this. These evolving technologies are going to drive how the PFAS regulation, unfolds itself in the next decade or two. The increase R&D is going to increase understanding. How is the appropriate way to regulate these things based on technology? How are they going to be managed when they're found out in the real world? As society increases its awareness of these things, of the PFAS generally, a certain subset of conscious citizens already are starting to pay attention and get a little nervous. But as it becomes more wide known, there's going to be more eyeballs on this, more tools are going to come, more litigation is going to come. Agencies are going to feel more pressure to regulate because of the increased, constituent attention on these things. So we do expect attention and innovation go hand in hand there. Product development in terms of raw materials, what you use in your supply chain, how you operate your business with using PFAS containing tools one way or the other, or products, and then corporate transactions like real estate or business purchases are really going to lean on the state of PFAS technology to make a risk determination for a future looking risk. And then overall developing or updating your PFAS compliance or PFAS risk management plan, I should say, is one of the priority recommendations we do make for clients, just to understand, put something on paper to help understand where your risks may lie, and if there's anything that needs mitigation, come up with a plan to address those. So we are right at 2. I think Brian and I